Chemical bonding 8. Metallic bonding. Metallic bonds involve a lattice of cations with delocalized electrons. The properties of metals are different from covalent and ionic substances. This is due to the formation of non-directional bonds with a sea of delocalized electrons. Metallic bonds. Metallic bonding occurs because metals have a low ionization energy. Metal atoms easily lose electrons. This helps explain metallic bonding and the properties of metals. There should be an S there, look. That's better. In a metal, the atoms lose their valence electrons. This leaves positively charged metal ions. But where do the electrons go when there is no non-metal? Well, the electrons are delocalized and they are free to move around in the solid. For example, this electron here might scooch between those two copper ions. This one might be swinging around the outside of that one, and this one might flow through there. They are free to go where they want. These free delocalized electrons are shared by all the metal cations. So, a metal has positive ions in fixed positions with a sea of electrons moving around. The strength of a metallic bond depends on the size and charge of the cations. Size of the cations. You can see a small distance between the positive nucleus and the electron there. The smaller the cation, the stronger the metallic bond. And this is because the distance between the positive nucleus and the negative electron is less, so the force of attraction is stronger. Conversely, you can see that electron being a bit further away from the larger cation. So the larger the cation, the weaker the metallic bond. The distance between the positive nucleus and the negative electron is greater, so the force of attraction is weaker. The strength of a metallic bond also depends on the charge of the cation. So let's look at this one. On the left there we've got cations with a positive charge, a single positive charge. And the distance between the positive and the electron is the same on both sides. But the smaller the cation charge, the weaker the metallic bond. The force of attraction between the nucleus and the delocalized electrons is lower than if there's a greater charge. Here we've got a charge of 2+. The greater the cation charge, the stronger the metallic bond. And this is common sense because the force of attraction between the nucleus and the delocalized electrons will be greater. If you think about it, the ions lost 2 valence electrons, so twice as many negative electrons form bonds as they roam between the positive cations, and those positive cations have a greater attraction too, a greater electrostatic force of attraction. Melting points reflect the strength of the metallic bonds. Here we've got magnesium with a very high melting point of 922 Kelvin. The magnesium 2+ ions have a greater charge than the sodium ions, so they have a greater electrostatic force of attraction, and so stronger bonds are formed. The greater the charge, the stronger the metallic bond. Potassium ions are larger than sodium ions. And the larger the ion, the weaker the metallic bond. And you can see there, the potassium has a lower melting point than sodium. Transition metals have stronger metallic bonds. This is due to the large number of electrons that can be delocalized from the 3d and 4s orbitals, or from the d and s orbitals. As we know, metals conduct electricity. The wires that we use are made of metal. If electricity is the flow of charged particles, and electrons are a charged particle, then if electrons can move freely through a substance, it's going to conduct electricity. And indeed, the delocalized electrons in the metal bonds are free to move through the metal, and so metals conduct electricity. Malleability. This means the substance can be hammered into a sheet. If you look here at the regular arranged cations with the little yellow electrons, the top layer has moved to the right. Now, when we looked at this with the ionic solids, they'd be brittle and they'd blow apart. Here, the mobile electrons allow the cations to slide around like ball bearings in oil, and they will still attract them. There will still be electrons between the positive cations. Alloys. An alloy is a mixture of two or more elements, usually metals. For example, steel. Steel is made of iron and between 0.25 to 2.5% carbon. It's used as cutting tools and structural materials. Gold alloy. 18-karat gold has about 25% silver in it. 14-karat gold has 58.3% gold, and the rest is made up of silver, palladium, copper and zinc, and obviously it's used in jewellery. Stainless steel, made from iron, chromium and nickel, and it's used in cutlery and sinks, and it doesn't rust because of the chromium and the nickel. And bronze is 88% copper and 12% tin, and again this was used in weaponry and in tools. Alloys are useful, and why is this? Well, they increase the strength and hardness of a metal, as we've seen before with stainless steel. It prevents corrosion and rusting, and it can improve the appearance of a metal surface. You can see here the bronze, it says that bronze was one of the first alloys created by humans. You see there, brass made of copper and zinc. I want to get on and talk about the non-directional bonding that occurs in metals. This means that the ion has the same attraction from all directions for the delocalized electrons. Right? Well, if you look here, you've got pure metal A and pure metal B, and they've been mixed together to make an alloy. The mixing of atoms here, which are different sizes, makes an alloy that disrupts the orderly arrangement of the atoms in the pure metals. So you see how orderly this is. Yeah, and how orderly this one is. When you mix them together, they're no longer as orderly. This reduces the ability of the layers of atoms from sliding over one another. Thus, an alloy is stronger and harder than its pure metal. Due to the presence of the non-directional bonds, the mixture of two or more metals can still be held together by the strong electrostatic attractive forces between the cations and the delocalized electrons. So the electrons can still move freely in and around here. It's not a problem, but the cations can't move as freely past each other anymore because they are not as orderly. That's it for this presentation, and here is an important message from Iron Man, whose suit is an alloy.